Okay, so now I got to part 2b. So what I will talk about now is some really like a new type of a problem I call term coding. So it turns out that this is like a unified approach to a lot of different problems you find in both network coding and the hat guessing, graph guessing games, and also something called index coding. And it's actually a new there's a lot of different research problems in this area. It's extremely rich, you know, so it's really lots of things you can do, and it links with finite model theory and equational logic. But the point is that while before what I showed in the previous section was that the link to equational logic was sort of straightforward in the sense that you can take problems in network coding and solvability problems and convert them to problems in equational logic. But now we are looking at some type of problems where you cannot make that direct translation. It's rather you're looking at equational logic from a new perspective. And then another highlight would be that I will simply show that most networks problems, I mean actually you can say except for some degenerate cases, I mean there are a number of, there's a certain type of obstruction, but if that obstruction is taken care of, you can always just do with one coding function. If you have a network that is solvable with many different coding functions, you can use one coding function that doesn't solve the network, but it achieves asymptotically when the alphabet goes to infinity, it achieves, so to speak, the right rates, information theoretic rates. And that's again fall out of the theory fairly easily, I would say. I hope, I mean at least it from the way we develop. So we look at okay, what is term coding? So we're given a system of terms like we did before, or if it's a multiple unicast relay network, the terms look like this. We have some terms, and we have n different variables. But now we're looking at a different type of problem. Let's look at the problem where we, instead of finding a solution to the network, want to see what's the maximal number of solutions we can find. So we simply ask, what's the maximum number of, over a finite domain A, we want to maximize the number of inputs that are being correctly received at the receivers. That's one way of putting it. So we don't want these equations to hold for all values in the domain, but just for the maximum number of assignment of the values. And there are other variants that are more close to information theory, maybe even more, where we require these different receivers. This is like a receiver sitting here. He has a term. He gets a certain function of the input, but he might want to get certain information about that input. He might be okay that he doesn't exactly know what x1 is, but somehow in the entropies, he has a very high entropy, high knowledge about x1. And also to basically determine the rate region for a given relay network is a very interesting problem. So, and we can look at the guessing games like before, where they have, remember we looked at these hat guessing games where each of them can see some of the other hats and then they have to guess what hat they have themselves. But you can also imagine they now have to play the game where some of the players are forced to use the same guessing function. So that's a kind of extra constraints that they have to, you can look at that. But you can actually phrase that, and also you can phrase a guessing game, you can simply phrase as this kind of problem where you want to maximize the number of solutions to some equations. So I think there are some examples that makes it more clear. So here's an example. Suppose we're given a finite collection of equality axioms. So then there exists a relay network which is in one-to-one correspondence between these number of solutions to the model, ignoring the auxiliary functions. So these constructions, I mean, was something you asked for. I mean, how do you actually convert these equations into, say, a relay network? But what you do is that you, let me explain, it's actually extremely simple. So the question is, how do you get from term equations to the relay network? So suppose we have one term, f of g of x comma y comma z equals x. I'm just doing it with the concrete values, but what we have here, this whole expression here is like a term. So that is t1. And let's say, so we have t1, this is just t1 equals x. That's one equation. But we might also have other ones. But how will we translate that to a problem? Well, the variables are the messages. So in this case, we have message x, message y, message z. And we have one receiver node that corresponds to the whole term that require the message x. So this message is required. But what is it doing? Well, we have a function. Now let's unpack. We have a function that calculates something from g and y. From x and y. So we have this one. We can introduce a new variable here, for example. But we can also think about it like this is just g of x comma y here. But this can equal a new variable. Let's say w1. And suppose we want to calculate how many solutions do we have to this system. Actually, to be able to solve it means that for any setting of the variables, there is a solution. But if we want to count the number of solutions, the observation is that if we make this substitution, v1 equals that for this node, it's like I can just replace the term equation with one equation saying this one equals omega 1, and then I take the other equation, I guess I just take the same thing here, but instead of this one, I now replace it by v1, comma z equals x. So now I have these two equations, but the number of solutions to the equation is exactly the same number as to the original problem. If you look at this, the variable z, w1 is, so to speak, forced to take one value, so it doesn't add the number of solutions. And now you do the same. Now this one we can give a name for another variable, v2. So we have f of v1, comma z, e2. That's another equation I add to the system. And then this equation, now allow me to make the change here on the board. We replace this thing here with w2, and we had a z here. So these three equations has the same number of solutions as the original system. Of course, these counting the solutions here is counting solutions x, y, and z belonging to A3, but counting solutions here is x, y, z, omega 1, omega 2, belonging to a to the 5. But it's the same number of solutions we have. But now if you actually draw a picture of this, you can see it's just a communication network. You have your z, and you have your x, and you have x, y, and z. Then you have a node. V1 is representing a node here inside the network. We have another node, V2, and then we have a receiver node down here that requires x. And now you just link them up the correct way. You know, you have g of x, y equals v1, so you have a function here. This coding function is g, you have sitting there. So that node is required to use that coding function g. Then you have f of v2 and z, that is, so wait a minute. That is x. So this one you get by computing these two. And finally you have f of v1 and z. So this node is being computed by the function f, a function f in this node. Do you see what I'm saying? So you can see it's actually, you just unwind the terms and you can write the network. And the observation is that the number of solutions you have to this system is exactly the same number you have here for this network. And so there's actually a one-to-one corresponding between finding coding functions to the term equations and solving the relay network problem. And it's the same, exactly the same trick you can also do for the hat guessing game. It's the same thing. I mean, you just so given a directed graph, we can actually rephrase the question of finding the best strategy over an alphabet of simply maximizing the number of solutions of this form. This is just essentially what we are doing here. So let me be a bit more specific so it's easier to follow. So here we have, let's look at the C5 again, a bidirected graph. But we looked at it before as a hat guessing game, where each node was assigned a hat color and you had to guess you your own hat, and all you could see was the neighbor's hat. But now in this example, we can see that as a part of a term coding problem, because we are given the variables x1 up to x5. Let me stress that, of course, from this problem, there's no reason why the alphabet have the same size for the different. They can have different sizes, alphabets here, but then you have to do what is called typed equational logic. So you can also develop that. There are theorem provers for typed calculus also, and so on. But I'm just doing it in the most clean case where it's all the same, so to speak. The variables belong to the same finite domain. Okay. Here are the equations. Does it make sense? We have a function sitting in 1. It's simply a function that takes the value of here, the head color, you see here, and the head color here, and it makes a guess. So this is like the guessing functions. And to be successful, that guessing function have to produce the correct value. And the players, what they want is to maximize the probability. They're all correct. That's the same as saying they want to maximize the number of solutions to this problem. So that's where it's different from ordinary equational logic. In ordinary equational logic, you want to solve all the equations over your finite domain. Here you just want to maximize the number of solutions over a finite domain. So the objective for the guessing game is to maximize this number of solutions. But of course, so this is the example. It turns out that you can actually, now because of the general formalism now, we can also look at the guessing games, but where they have to use the same guessing function. So now, look, now the equations are essentially like before, but each of them have to apply the same guessing function. It's just to show what the formalism can do. And in this case, you can actually prove that that's enough. They don't need to use different guessing functions. They can actually, if the size of the alphabet is a square number, they can use the same guessing function. If it's not a square number, for other, there are examples where they can do better if they have different guessing functions. There's a symmetry breakdown. The symmetry breaks down, so you cannot assume that just because a network is symmetric doesn't mean that the solution has to be symmetric. The solution can be asymmetric. So here is a remarkable simple proof, but it's something I have done here while I'm here at Nexus. So we have a network coding problem, and assume it's solvable. So let me see. So we have some inputs, let's say x1, x2, x3, xn. We have some acyclic graph representing the network, and then we have some receiver nodes here, say in the bottom. This one, say, receive x1. This one receive x2, and we can actually also make some of them this one might also receive x1 again, you know. But let's just for simplicity in the setup assume each one just have one demand. It just want one of the inputs. This one maybe one xn. So in the network coding solvability problem, we are simply asking, can we find coding functions that solve this problem over some finite alphabet? Okay. And in the network coding problem, normally you can use any coding functions in any node you want. So you don't have to use the same coding function. But I claim that essentially we can use one coding function. It's a very simple argument. If you compromise a bit, so you are not requiring that you get full solvability, but you basically require that each receiver can get a lot of information in a limit, can so to speak get full information about the message being sent. And the argument is actually fairly easy, but let me first explain the obstruction to this thing. Actually, let me see, is that now I'm even giving the proof, I think. Oh, maybe I can give it now, sorry. So the proof is remarkable. Yeah, I have this notion called D-array coding, the single D-array, and that is not G-generated. That's a technical term, but let me just explain. I think intuitively it should be pretty clear what's going on here, because there is a simple obstruction to hope. When can we not hope to use the same coding function? Well, suppose we have X here, and we have Y here, and we have a network that looks like this. So here we are setting some coding function, And here maybe we require the message x here. And this node, we have, again, some coding function. In a normal network coding problem, we have some other coding function here, and maybe here we require a message y. Now, according to the normal way of solving it, it's very easy. We just send x this way, and we send y this way. But suppose now that this is a function, f of x comma y, we have, and we use the same coding function here. Then clearly we are in trouble, because these are the same messages. This is the same message. And clearly from these two messages, you cannot both construct x and y. It's simply a violation. So that's not possible. Well, in this case, it turns out you can actually still do something, because you can, for example, apply x comma y. You can swap the arguments here when you store it. So, you're using the same off-shelf, so to speak, coding function, but the way a node applies could be different. So here he applies them in different order. And then in this network you are fine. But what about if there was another node here? Now you're really in trouble, because this node, again, a function of two variables, you can see x and y, but now it doesn't matter if you have f of x comma y or f of y comma x. You are simply stuck. I mean, so here is an example of a network. You can build up a network like that, where you clearly cannot do with one coding function. There's an obstruction to it. And the obstructions, let's just be simple and simplify the obstruction a bit. You can see from the proof, actually, what the real obstruction should be. But the way to simplify it a bit is to say that a node dominates another node if you can see at least as many inputs as the other node. So for example, these two nodes, this node dominates this one in the sense that this node can see, in this case, the same number of nodes as this one. But suppose we have a network where this is not the case, so every single node can see something other nodes cannot see. That would be one example of a non-degenerate one. Yeah, simply see. That means that if you look at all the predecessors of this node and this node, it turns out to be the same set. What we don't want to have in general is that the predecessors of a node V1, we don't want that to include the predecessors of a node V2. We don't want that to happen. But even if that happened, it turns out you can still deal with that by then shifting around the arguments. But just for the argument, you can cover that, and you can also, of course, as another obstruction, you might have a function that is d-area somewhere. The arity of all these incoming ones could be different. So what do we actually mean by using the same coding function if you have different arities? So what would you suggest? So I mean, one natural way is simply to say that you apply just the first arguments, and the remaining arguments where nothing comes in, you just put a 0 or some fixed symbol. You're not allowed to, you just put a default symbol for the rest ones. So do you want to hear just a brief outline of the argument why you can do it? I mean, it's remarkably simple. So yeah, that's the slide. Yes, you want to see that, of course. So what happens is actually very simple. So what we have is that we have, how can I best describe it? Yes, suppose, so the setup is that we now assume we have a solution to the network coding problem. So here we have a demand, and we have a solution. That's important. And when I say solution, I mean exact solution. There's nothing about epsilon solution or anything. I really require that every single receiver exactly know the demands. Otherwise, the argument breaks down. So we require that there is an exact solution. Then I hope you will agree that if all these different nodes, we just change the alphabet. So instead of they work on, in a moment, these are messages from the same alphabet. What I want to show is that I can choose a constant fraction of all the inputs on which all the demands are met. Just a constant fraction. But then when I let the size of the alphabet, I do normal coding theoretic considerations and let a go to infinity, then when you take the logarithm or you look at the rates, information rates, it becomes, you can essentially, it converts to 0, basically, the loss of information. So let's, so a split, so this at the moment is from the same alphabet, and each of the coding functions here are calculating some functions, but they're inside the same alphabet. But of course, when you have such a solution, there's absolutely nothing special about two finite sets. I could replace that alphabet by another finite alphabet of the same size. Of course, I just modify the functions a bit, but I mean, if these are green numbers, originally were just normal binary numbers in some range, and now I color them green and think about them like a different alphabet. So the first step is just simply to take the input and assign to them different domains. So what I'm really doing is I'm splitting A into a finite number of parts, disjoint parts, and they have roughly the same size. And each part is just like, you can think about like the alphabet. Actually, maybe that's a bit confusing to say I'm splitting A in, but I mean, okay, you can think about A like the, okay, so maybe I say B is a new alphabet that is going to be the one I'm going to construct, and it's built up by all these colored different alphabets. I split, I take A, I now solve the problem, but where all different inner nodes are using different alphabets. And the output, if you require some variable here, some variable x1, of course you're using the same part of the same copy of the alphabet as you're using here. And then I define the new super alphabet I'm using for the coding function is just simply the union of all these ones. So each of those alphabets is just being built up from having a finite, what can I say, they're built up from these parts of the alphabet. So we know we have a solution from the network coding sense on all these parts. So now we want to build up our super coding function based on this set. But it's very easy to define, because when he calculates, he's sitting in some node and he calculates something, all it has to make sure is that if this one belongs to the correct part of the alphabet and this one belongs to the correct part of the alphabet, then we know what the value should be. We just assign it that value that it should have from the solution we had on from the network coding case. And because we don't have this obstruction from before, each of those nodes are seeing different things, so we never get into a conflict where we suddenly have to have another node to see the same one, and we cannot, because then the argument breaks down, of course. But as soon as there's something in the argument that is different, there will be a part here that belongs to another part of the alphabet. We will never get any problems and can just assign another part of the alphabet to that node. Does it make sense? And then the point is that that's just so you can see they don't achieve the limit, but it's like Shannon's coding theorem, you know, that you don't mind that they can only do it on a fraction of the inputs, because you just let the alphabet size go to infinity. So that's okay. So that's.
I would not say that it is a simple, by the way.
What do you say?
I would not say that it's a simple idea.
You don't think it's a simple idea? Maybe it's not simple. Thank you. I'm very pleased. You say that's a kind of you. I think maybe it's. Yeah. Okay. Thank you for. So it's not simple, but of course it is always like. Well. Okay. Yes. Okay. So let me see. How much time do I have? So I think I have time to do a little bit of 2A, and I want to show that because this is really neat, but I can probably do it in 10 minutes, at least give you the basic idea, and then I think we are reaching the time, is that right? Or it was kind of predictable that I had too much material, you know, and so what I want to do here is look at the, let me see, here. Yes.
So the transform you did, now the sources are different from the edges. So it's as if you brought them all down and you kept the rates on the edges 1 or something, right? Because you're not allowed to excite on the full alphabet on the source anymore in the big product alphabet.
No, I mean, you can put it this way, that of course in order to utilize this communication network, you will probably do some encoding up here, so the message X, since these have to, for it to be successful, these ones, the messages you're sending have to belong to different parts of the alphabet, but you can kind of enforce that, for example, by encoding, or you can have error correction. You can do a lot of things. You can also do header bits. I mean, it's all in a big paper I did a few years ago, so it's this idea of, we call it dynamic routing, where the headers are, so to speak. You have you reserve a little bit extra space for the headers, so they keep track on that. Then you can. It's essentially the same idea you're using here. But let's talk about it outside, because it's quite technical. I mean, there are lots of. One has to be precise here about exactly what is being proved and exactly in what sense can the receivers actually get full information about what they receive. One has to be. So maybe I should just state the theorem, at least here, as exactly what I proved. Is you can divide all the input into a finite parts, such that on that finite proportion of all the inputs, everybody gets the correct message, so to speak. Okay, so I want to say a little about what happens if you have infinite alphabets. So we are doing linear network coding now, but suppose the alphabet is infinite. And it turns out that there are lots of tricks, lots of things you can do if you have infinite alphabets. You can easily, I mean, I'm now in a linear setting, so I assume that we have, say, a ring or something like that. But we can have a situation like this. So we have a message x here from the ring, and we have y from the ring. And maybe here suppose here we are computing a linear combination of these two. That means we have one ring element R1 times x plus another ring element times y. So this is in itself a ring element. This element is then being broadcast to these two nodes. And suppose this node requires x. That means we have an equation x equals R1 x plus R2 y. That would be like we are solving that problem. But this is like the butterfly network without wings, if you notice. There's no. We shouldn't be able to solve this problem intuitively if you want to. It sort of violates information theory in some sense. So it violates the notion that we have sort of a fixed bandwidth. We cannot just cram in lots of extra information. So in some sense, if this one is satisfied, this part is forced to be 0, first of all. So you can put it this way, that if you write down it as an equation, you can say if R, actually we have to decode here, so you can say x equals, I should say, some decoding of this one, but the decoding would be a linear function also, so that would be d times this expression here. So in order to solve the problem, d times R1 as ring elements have to be 1, and on the other hand, d times R2 is 0, because obviously that's the only way you can get the message x, that is if d times R2 is 0. But from this you want to conclude, it's simply not fair to expect that R2 has to be 0 itself, I mean. Because if R was not 0, you could actually in that node not only receive x, but you could get some information about y at least. Do you agree? So we should have that if this one is satisfied, then this one is satisfied. And that is what it turns out that is equivalent. This is a condition I just wrote down. That is called the capacity condition. This is a very natural condition to write down. It's simply saying that if x times y is 1 and x times z is 0, then we can conclude x is 0. That's exactly this kind of requirement we have here, that we are using the full channel. There's no extra space in the channel. Of course, because rings are infinite, you can easily find rings where this is violated, where you can. But this is a capacity condition. Now there is a very famous class of rings called Dedekind finite rings. They also go under other names like von Neumann finite or directly finite rings. And these are rings where if an element has a left inverse, it also has a right inverse. And it turns out that this is equivalent. So here we have a number of different equivalences I proved, but many of them are known. But this definition, the capacity condition, I couldn't find in the literature. So it seems to be sort of a different way of, probably it's not so natural for mathematicians to write it like that. But nevertheless, it's equivalent to being Dedekind finite. What I want, I don't think I have time. It's a pity in some sense I don't have time, because I ran here, because I expected that I wouldn't have time to do it on the blackboard. And also, you probably trust the theorem prover more than me, so I could just run it on the theorem prover and actually prove the different implications here. So actually all of these implications I can verify just on the theorem prover. But there's some interesting things here going on. I will actually skip it now because it takes some minutes to run. But the point is that it actually gets stuck on some of the implications. So some of the implications it can do. The hard one for human, I remember when I was doing that part, that was the most difficult for me. And it took me some thinking. It was a very short argument, but it was difficult for me. It turns out that for some reason it's also hard for the theorem prover. It's the only one that it takes significant time to work it out, I mean, compared to the other one. And the theorem prover cannot, within a few minutes, prove that my capacity, the capacity condition implies Dedekind finiteness. It cannot prove that. It can only prove it if you help it by these lemmas, then it can prove it. So it shows us some limits. I mean, the human can still, so to speak, help the theorem prover sometimes, you know. So here is a network which is interesting because now you can now we look at networks, but we look at equational logic, but we look at solvability over Dedekind finite domains. This network is, you can say now imagine we are doing network coding over Dedekind finite ring, and it turns out that this network has a solution over Dedekind finite ring if and only if 1 + 1 is 0. One way of interpreting this is to say, imagine we are sending, this is a communication network, we have some fixed bandwidth for all these communications, and these are requirements. Imagine that imagine that we are working over some digital strings, so it's binary somehow. Then if you work over binary strings, you can clearly, it makes sense to say 1 + 1 is 0. So that is, on the other hand, if we are talking about analog signals, function space or something like that, then we would not expect that 1 + 1 is 0. It cannot happen actually. So this network, one way of putting it is that this is a network that doesn't have solutions in an analog setting for analog signals, but it has solutions in a digital setting. On the other hand, you might ask, of course we know that digital communication is always better than analog, isn't it? I mean, analog is something we have given up a long time ago, and clearly the information you can get through by analog is worse. But actually from this purely theoretical point of view, actually here you can also verify. This is, maybe I will verify this. So just a moment. So now I'm actually verifying that this equation, these are the ring axioms I have here. Actually, I've added a few extra idiotic, unnecessary ring axioms just in the hope that it was a bit easier for the what do you call it, from the which one is that? Is that? I think that's the wrong one. Just a moment. Just a moment. Yeah, let's do that one. So here we have the ring axioms. Oh, it looks like there's some problem. This is the theorem from before. So it looks like the media file. It's somehow running the wrong media file. Okay, so I don't know. Anyway, we are running out of time, but let me just explain what is happening. And I can show it to people if you want to see it, so to speak, live. This is quite curious. If you actually solve these equations, you can write down all the requirements you have here as linear equalities. And it turns out that if you run it and assume that the ring is Dedekind finite, you exactly is solvable if 1 + 1 is 0. On the other hand, if you look at this network, it's exactly solvable if 1 + 1 has an inverse in the ring. So that's exactly to say if you're working over somehow digital signals, somehow you shouldn't be expected to solve it. And one can also go further than that, and I'm doing that in the paper, to say, but maybe that is just a purely academic thing, because maybe the rate there is between solvable over fields of characteristics 0 or fields of characteristics non-zero, or rings. These different rings are so minute difference, but you can actually show that there's a bigger gap. It's like about 75%. That it jumps from. You can actually do some with some extra assumptions on the rings, you can prove some other results. To tell that the rate, if you use linear coding, is actually significantly different between the different networks. So I think that's the end of my talk. And any questions? Or? Thank you.